Welcome to Let's Talk Energy. Let's Talk Energy is a production of the National Energy Technology Laboratory. The Energy Lab is one of the U.S. Department of Energy's 17 national labs. Your host is Joe Culver.
Thanks for joining us for Let's Talk Energy. We're at the National Energy Technology Laboratory's Albany research site today, talking with Dr. Paul Jablonski. Hi, Dr. Jablonski.
Hi there.
Tell us what you do at the Energy Lab Albany site.
Well, I'm a metallurgist in the process development division here in Albany.
You develop processes for what?
Well, we develop processes, develop materials. These are all energy-related materials, so we're trying to extend the operating temperatures and operating lives of materials that are used in energy applications.
You're out here in Albany, Oregon. Have you always been a part of the NETL laboratory system?
No, we became part of the National Energy Technology Laboratory in 2005. Prior to that, we were the Albany Research Center.
And even before the 2005 joining of the labs, you were part of the Department of Energy, though,
That's
I believe.
correct.
And you're sort of the materials part of DOE.
That's our main focus here at the laboratory, is developing materials.
And those materials and how they tie into energy, because the materials you develop really go into energy systems, isn't that correct?
That's correct.
Okay, now your history, you've done a number of things, but some of what you're doing right now is in alloy development. And I understand that you're using a computer-based process that relates to alloy development. How does that work?
Well, we like to evaluate our materials with computer-based alloy development tools prior to formulating and melting and fabricating them. It's a much more efficient way of designing materials for energy applications.
How does a computer manage to assess that process?
Well, just recently, we used a combination of computational thermodynamics and a mobility program to optimize the heat treatment of cast materials.
In order for the computer to do that, do you have to input a lot of information about the processes and the heat treatments and the thermodynamics?
Absolutely. It takes quite a bit of background and development in order to do the computational work.
How do you come up with those data that you're able to put into the computer?
Well, actually, it's a combination of a lot of researchers' efforts over the years.
And what did they do? Did they just go out and melt a bunch of metal? And how did they come up with that information?
A variety of techniques. Some are based on work with simple binaries, but it's actually a culmination of 30, 40 years of work.
Now, the particular process that you're involved with right now, what is the end result of the materials that you're developing?
Well, we designed a optimized homogenization heat treatment for cast materials for the ultra supercritical steam turbine casing materials. That's because these are very advanced nickel-based superalloys that are prone to segregation, but to be able to utilize the full potential of the materials, you need to homogenize them. Now, these materials are not typically used in the cast form, so there was no basis upon which to perform the homogenization heat treatment. So we optimized that with the computer-based programs and then tested it out in the lab, and it really seems to work.
You said these are for steam turbines. Now, they've used turbines driven by steam for a long time.
Yes.
Why do we need to have a new material?
Well, these are ultra supercritical steam turbines which operate at temperatures and pressures above the operating conditions that the materials that are currently used can operate at.
A current material, what would be the heat environment that we would use it in?
Oh, they would be about 500 degrees C or so, and typically they're iron-based stainless steels. These materials are nickel-based superalloys, and they're able to operate upwards of 760 degrees Celsius.
So how do you make the steam get 200 degrees hotter?
You just heat it hotter.
Really?
Yes.
With what?
It's a coal-fired power plants.
Oh. And so, and why do we care if it's hotter steam?
Well, these are very advanced power plants, and the potential savings in efficiency and reduction in emissions are just tremendous. The operating efficiency are upwards of 60%, which is unheard of. The traditional steam turbine power plants are operating around 35% efficient. So that's going to reduce the amount of pollutants produced and reduce the amount of energy consumed.
Because they're running more efficiently?
That's correct.
You've discussed how we're trying to homogenize these materials, and I think that requires a step in heat treatment. Can you tell us what is heat treatment and why is it important to the process?
Sure. The way I would like to tell this story is that solidification is inherently an unmixing process. So you start with the new alloy that you're trying to formulate, and you melt it. It's nice and uniform and fully mixed when it's in the crucible in the molten state. Then it's poured into a mold, and in the process of solidifying, it actually unmixes. Now, this is a problem because you don't have all of your alloy constituents exactly where you want them throughout the structure. So what we've done is we've developed a computer-based homogenization heat treatment optimization process where we take the alloy formulation and we predict the amount of segregation that occurs during that unmixing process, during solidification. And then we characterize the microstructure, the scale of it, and then heat treat, if you will, the material within the computer and really optimize the heat treatment process. So by doing that, what we've done is we're able to reduce the amount of time in the furnace, which is what the homogenization heat treatment process is, and really redistribute the strengthening elements and the corrosion resistant elements that we put in there to do specific jobs for the alloys.
If I understood you, you're developing a material for a turbine to function in an ultra-critical steam environment, a much hotter environment. If we were to take a turbine that we're using in the environment today, which you said is around 500 degrees C, and put into that 700 degrees C environment, how long would it last?
Well, you know, frankly, it's just not going to operate at all. It's going to be a matter of hours or so before the material just disintegrates.
And so it would essentially be useless.
Correct.
How long do they last at 500 degrees?
At 500 degrees, they last an awful long time, on the order of 30 years or so.
Okay. Now, the new material that you're developing with your computer-based approach, once that material is perfected, if that's the right term, and you make a turbine and put it into a 700-degree environment, how long would it last?
The goal is 30 years as well for that material.
Which is approximately the lifetime of that system.
Correct.
And would someone then go in and refurbish the system, or at that point is that system no longer usable?
It could be refurbished, yes.
Okay. We're in a fabrication room where there are a lot of machines that you use in your fabrication process and your alloy development. When you began to make a material and produce it, like these turbines we've talked about for high temperature environments, what is it you have to do to make those things actually work well?
Well, first we start with computer-based designs where we optimize the alloy formulation based on some thermodynamic programs to look for phase constituents, and we're really trying to develop an alloy for a particular application. In this case, we're looking at a much higher operating temperature than is currently being used. The reason for the higher operating temperature is that that gains us quite a bit in operating efficiency, reduces the amount of fuel we need to operate a power plant, and reduces the amount of pollution that's developed as a result of burning the fuel.
When you talk about a power plant, you're talking essentially a coal-fired power plant?
Yes, essentially a coal-fired power plant, but in general it's applicable to any type of process which creates steam and then converts that into rotating energy to create electricity, for example.
From looking at the energy aspects of it, if we increase the operating temperature from 500 to 700 degrees or 800, wherever you can go with it, what's the effect of that on efficiencies and on the power plant operation?
It's very substantial. The current power plants are operating at about 35% efficient, and with this increase in temperature and increase in pressure, the efficiencies are upwards of 60% or so. So that's quite a gain in efficiency, as well as a reduction in the amount of CO2 that's produced, for example.
One of the goals in the materials development arena is to be able to somehow get past the steps of throwing in some material and melting it and see what the properties are, and then throwing in some more and melting it. You've talked about computer design. Is our goal to be able to design materials using computers?
I think that that's a long-term vision, but in reality, there's always an aspect of testing out the theories. And that's one of the things that we do in this laboratory here, because it's nice to be able to design an alloy on a computer, but you actually have to get in the lab, make the material, melt it, and homogenize it, fabricate it, then expose it to application relevant conditions of temperature and stress and environment to really find out whether the theory meets with the application and meets with reality, and if the material will perform.
So it sounds like a while before we actually will fill this room with computers and take out the furnaces and the rolling operations. And
It could be quite some time, yes.
and so folks like you are going to have a job.
Well, I think that the computer-based alloy designs is not so much a replacement for the old school techniques, perhaps sometimes are referred to as an Edisonian technique, but they're actually a new tool to help refine and dwell into the types of alloys which will be much more effective, much more producible, and will perform better than just simply a trial and error technique. Some of the alloys that we're looking at right now have upwards of 10 or 12 alloying constituents, so that becomes very difficult in a matrix to try and add a little bit of this and add a little bit of that, but you can actually do that pretty effectively in the computer. Of course, then you need to go out there and test it.
Dr. Jablonski, I think of the work that you described sounds very important, and I hope that you can come up with these turbines. That sounds like that will contribute not only to efficiency, but it will contribute to a cleaner environment and probably a better energy future for all of us, which is what the Energy Lab is here to do. Thank you so much.
Thank you.
We've been here today with Dr. Paul Jablonski at the National Energy Technology Laboratories Research Center in Albany, Oregon. Thanks for watching.